Okay. So let's go to the PowerPoint. Where's the PowerPoint? Okay, so you can see the PowerPoint. Okay, so far we learned about work, energy, power. We learned about the introduction of energy, all type of energies, and we heard about energy crisis. First, what principle of conservation of energy say? Energy cannot be created or destroyed, only can transform from one type to another. Okay, remember the principle of conservation of energy. Then after we talk about the plus and minus of all sorts of energy, we talk about work. What is work? Work is the product of force and distance travel to the direction of the force. Don't forget to say the word to the direction of the force. Most of the students just saying that work is force time distance travel. That's it, full stop. You might lose 1 mark. You must say force time distance travel to the direction of the force. Okay. Okay, so we did some examples. Okay, today's class, we're going to start with the examples. Okay, so this one question, give a try. 1 minute for you, all about work. Okay. So get the answer as shown down below there. Get the working, get the answer below there. Okay, just warm up, understanding your work further. The work can be negative. When the work can be negative, when the force and distance travel is opposite direction, work is negative. Okay, so you have to put negative. Horizontal force of 90 Newton is used to push a box. On a horizontal floor, the frictional force of the box is 50 Newton. And the box is moved through a distance of 6 meters. What is work done by horizontal force? Okay, what is the work done by the horizontal force? So the floor is, there is a box pulled by 90 Newton of force. Okay, and there is a friction acting backwards, which is 50 Newton. Okay, but finally it was dragged for a distance of how much? 6 meters forward. 6 meters forward. So finally the box is here. So they're asking, what is work done? What is work done by the horizontal force? So horizontal force is what? The 90 Newton. What is work done by the 90 Newton? So of course, 90 times what? The distance traveled to the direction of force. So 6 meters. So 90 times 6. So you should get 550. Okay, then next. What is work done by the frictional force? Frictional force is 50 Newton. Okay, 50 Newton. But displacement and the distance travel and the force is opposite direction. So therefore, we put negative 50 times 6. So negative 300 joule of work has been done. 300 joule of work. Negative 300 joule. Negative work means it gives a negative effect to the system towards the end. It's going to reduce the mechanical energy the body possesses. Okay, like brick always does a negative work. Okay, it does work because it applies force and there is a distance travel to the direction of the force, but finally it's a negative work. Why? Because the car going to slow down. Its mechanical energy going to drop. Give a negative effect to the object in terms of the amount of mechanical energy possessed. Okay. So next, what is the next work done on the object? Okay. So the 90 Newton of force did 540 joule of energy work, and friction does 300 joule. So the net work is minus them 540 minus 300. That's the net work. Okay. So 240 joule. Okay. So what is meant by net work? Net work done means this the result, the net work done. Okay, net work done is the 240 joule is actually finally is the positive work done to the object. So the 240 joule going to be the gain in mechanical energy of the object. Mechanical energy means gain kinetic or potential. The net gain is 240 only. A car moving forward with 90 Newton, but friction did a negative work. Therefore, the net work is only 240. So the car only gained kinetic energy of 240. Less gain in kinetic energy. So the change in kinetic energy of the box is have to be same as 240 joule, because the net work done is the gain in kinetic energy and potential energy. But in this case, because the flat surface, so no gain in potential energy. So therefore, potential energy gain is 0. So all change to kinetic energy. Okay, so 240 joule. So net work done is the gain in mechanical energy of the object. Okay, so I think all this need to be highlighted here. Work can be negative. Okay, when the force and distance travel is opposite direction. Okay, any question, you just on the mic and you can ask me immediately. Okay, so any question from this slide? No problem. Okay, we move on.
The change in energy is the same as the network.
The gain in mechanical energy of the body. The gain in mechanical energy of the body is the net work done.
Okay.
The mechanical energy is what is inside the mechanical energy can be EP and also EK. EP, EK is the mechanical energy. But in this case, EP never rise because of flat surface. Okay. Okay, so now we see work done in a different form now. Okay, this car cylinder, the engine cylinder, the pistons moving up and down. Okay, so the piston, the gas here, the fuel flew into the cylinder, and later the spark plug will produce a spark, burns the fuel. So the gas produced, the explosion produced up in this region, expand the gas. When the gas expand, the piston move down. So the expansion of gas involving work. Okay, the expansion of gas causes work done. Okay, so now when a gas expand, what is the work done formula for the gas? So this is the work done by a gas formula. Okay, this is the work done by a contact gas formula. When a gas expand, you see the first body here, the first body here. The gas is, this is the volume of the gas. This is the volume of the gas. When the gas volume is increased, moved up because of explosion, maybe the gas expand, moved up. So it does work. The work done by the gas is the force exerted by the gas times the distance travel, F times D. So work done by the gas is F times D. But in terms of pressure, the force you change to pressure is pressure times the area. The cross-sectional area times the pressure is your force. The pressure times area times the distance, vertical distance travel is the work done. But the area times D, the cross-sectional area times the D, is actually the changes in the volume of the gas. So finally, work done by gas formula is P changes in volume. Or in other words, if you plot pressure versus volume graph, the area and the graph, is the work done. Okay, so if the pressure of the piston is constant, the area and the graph going to be a square, so it's going to be P changes in volume. But if you go for further studies, the work done by the gas, they won't put in these P changes in volume. They'll put in terms of integration format, P dV. This is the best way of writing the work. Okay, the integration of P dV. Last time I think most of you did for the additional maths. So integration y dx. If you do y dx, that means if you plot a graph y versus x, what is y dx integration stands? Let's say we have a graph like this. So y dx, integration of y dx actually what? The area under the graph. The area under the graph. So now P dV is what? If you have a graph of P versus V, and let's say the pressure is changing irregularly. So what is work done by this expansion of gas? The area under the graph. The area under the graph. So to be more proper, we put in the integration formula. Okay. But in your syllabus, the uneven change in pressure won't happen. Okay, a curve won't happen. But normally in your syllabus is only a straight line. That means your syllabus only constant pressure. Pressure is said to be constant. So you're going to make a yield a square. So we put P changes of volume. Okay, let's say Cambridge, we cannot trust Cambridge. Sometimes they give a different graph. Let's say they give P versus V. The graph given is like going up like this. And they're asking for work done. What is work done? You must know the area and the graph of PV is the work done. Okay, put in your mind, the area and the graph. Following this formula, integration of PdV is your work done. Okay, so new formula for work done for gas, expanding gas. P changes in volume. If there is a changes in volume, there is work done by the gas. If the volume of the gas does not change, no work done by the gas. Okay, any problem in this slide? Understand? Work done by gas is P changes in volume. Okay. Okay, so one example, you see here, how much work is done by gas if it expands from volume this much to this much at a constant pressure. So work done is P changes in volume. Okay, so final volume minus initial volume, so times the P, so you get is the work done by the gas. So if this gas is trapped inside the engine cylinder, so engine cylinder will gain this much of energy, maybe in form of it has gain in the mechanical energy. You might use this energy to gain in the mechanical energy, either in kinetic or in the potential form. Okay. Okay. So that's about work. Okay, we're done with work already. Okay. So now we're going to talk about kinetic energy. Okay. We know kinetic energy is a type of energy possessed by a moving object, half mv squared. Okay, Ek is half mv squared, mass times speed. Okay, now what extra they ask in A levels is how scientists found the kinetic energy is half mv squared. The derivations you have to know. So how they derive E equals to energy equals to half mv squared. How do you derive it? So they use some theorem called work energy theorem. Whatever work done by a force is converted to energy. Okay. So when an object of mass m is being like this diagram, an object of m being acted by a force of F, so that the force accelerates the object from initial velocity to final velocity through a distance of a. So you have an object. Let's say you apply a force F. Okay, it was rest. U was in rest, so U was 0, and you apply a force F, and you drag a distance of s, and the object is finally here now. And it attained a velocity v, okay, attained a velocity v after travel distance. So they said the final velocity v through a distance of s. So the v, u, a, and s must link to this formula. V squared equals to u squared plus 2as. Okay, v is the final velocity attained. U is the initial velocity, but we take it as 0. A is the acceleration, and s is the distance it traveled. Okay, if you multiply all the equation with mass, it's going to be mv squared, mu squared to mas. So mas is equals to half mu squared, half mu squared. Okay. Okay. So what is mas here? From work done by force, Fs is mas, right? Fs is mas. So mas is actually the work done. The work done is converted to, in this case, purely kinetic energy. So this is the kinetic energy formula they found. So work done converted to gain in kinetic energy. No potential energy here because we slide it in a horizontal surface. So the mechanical energy gain is just kinetic energy. So the work done is actually changes in its kinetic energy, But if we start with initial velocity 0, then changes in kinetic energy. Work done is the changes in kinetic energy. Okay. So the net work done is change in kinetic energy. This is the final conclusion. If the initial velocity is 0, then the work done is equals to half mu squared, just the kinetic energy of the body. Okay. So this is how you derive the kinetic energy formula. So the principle is what? Work done is the one converted to energy. That means F times S is the gain in or change in kinetic energy. Okay, this is the concept we based on. So by using the kinematic formula, V squared equals U squared per 2AS. So we want to create MAS in one side. That's why we're multiplying with mass. MAS we know is Fs. So that means this should be the gain in kinetic energy. So we got the kinetic energy formula of mv squared. Any question from this slide? This is a 3 marks question to derive kinetic energy. Okay. The story here, they might tell you, you must start with the kinematic, 1 mark. You must multiply the mass, must show this, 1 mark. You must tell MAS is the work done, 1 mark, then final formation. Okay. So something new, you never learned this before. How they got half mv squared. For work, they got the kinetic energy formula. Okay. So this all going to be an easy exam, easy question. The speed of a dog sleigh of 80 kilogram moving along a horizontal ground is increased by 3 to 9 meter per second over a distance of 9 meter. Find the increase in kinetic energy. So what is increase in the kinetic energy? The work done by the force. Okay. So 90 meter increase in kinetic energy in this case just half mv squared minus half mu squared. Okay. So half mv you put 9 and you put 3 squared. So you get 2.9 kilojoule. What is the force exerted on the sleigh by the dog, assuming there is no resistance, no resistance, no frictional force, no air resistance? So what based on you can get the answer for the B? So you see the net work done, okay, the net work done is equals to the gain in EK. That's the principle we based on. Gain in EK just now we know is 2.9, so it's 2,900 joule. So work done is force times distance travel, so we can find the force. Okay, so force times, of course, force equals to 2,900. 2,900 divided by the distance travel, which is how much? 90 meter. I will give you the force applied. Okay, get 32 Newton. Okay, 32 Newton. Okay, so new idea. The net work done is the gain in kinetic energy for this case. Normally it will be gain plus EP also, but because it's a flat surface, EP does not involve. The work done, the net work done is the gain in kinetic energy. Okay. Any question from here? No, Okay. Now your turn. A 2000 kg car traveling at 20 meter per second comes to rest on level ground at a distance of 100 meter. What is the change in kinetic energy? How large is the average frictional force tending to stop it? So first, what is the change in kinetic energy? So kinetic energy is the net work done. Is the net work done. The net work done is how much? 400 kilojoule. How do you get 400 kilojoule? The EK, the changes in EK lah. The changes in EK is final kinetic energy minus initial kinetic energy. What? Final kinetic energy is 0. Initial kinetic energy is so the changes in EK, how do you find? Half mv squared minus half mu squared. Okay. So half mv what? 0 squared, final velocity is 0 minus half m initial velocity is 20 squared, and the mass is found to be 2000. Mass is 2000. So what do you get? So you get yeah, half mv squared, 20 squared, 1000. So you got 400, 1000, so you get 400 kilojoule. Okay, you got 400 kilojoule. Of course, negative. Why negative? Because the kinetic energy dropping. Kinetic energy dropping. How large is the average frictional force tending to stop it? Okay, we know that kinetic change is kinetic energy is the net work done. The net work done is the frictional force. Frictional force does the work. Force times the distance travel, frictional force. It should be negative 400 kilojoule. Okay, so the force you can find, the force is negative 400 divided by the distance the friction applies, 100 meter. So because drag for a distance of 100 meters, so you get frictional force is actually 4 Newton. It's like 4 Newton, negative 4 Newton. Negative terms is opposing force. So negative turn is by the friction. Negative for the Fs. So F you get 4 Newton, 4,000. So it's 400 kilojoule, right? 4 kilonewton. So 4,000 Newton. Okay, so this is how the working should be. Okay, the gain in kinetic energy is negative, so the force you'll get will be negative, but you take it as positive. So frictional force is 4,000 Newton, only the magnitude. Okay, that's about kinetic energy. Something new is what? The derivation of kinetic energy formula you have to know. Okay, that's something new. Okay, next, potential energy. So potential energy is the energy possessed by a body due to its position. The definition. You drag up, you gain potential energy. You compress the spring, you get elastic potential energy. There are many types of potential energy. GPE is the most famous, gravitational potential energy. Potential energy gained through gravity. You have elastic potential energy. Due to elasticity, you get potential energy. You have electric potential energy. A potential energy gained due to electric field. It's called electric potential energy. So there are different types of potential energy. But the one is the most important, the most famous one is the GPE and elastic potential energy. Okay. So GPE. So yeah, positive to negative, no GPE. Okay. So magnet. So this also potentially due to magnetic field. Okay. Now we want to get how scientists found that gravitational potential energy is mgh. How they get the formula mgh, the derivation, you have to know. Like kinetic energy, how you know the derivation. For potential energy also, you need to know how to derive it. Okay. An object of mass m is being raised to a height of h2 from h1 without any change in kinetic energy. So let's say you raise an object from here to here for a certain height h1 to h4. The work done by the force is F times S. Okay, like you are bringing this object from down to up. Okay, h1 to h2. The work done by you is the force you apply up times the distance you travel from the bottom to up. So force that applies the weight of the object. Yeah, to pull the object up, the least amount of force you need to apply is same as the weight of the object. Okay, so thus the work done is mg times the height you rise long. So h2 minus h1. Maybe h1 you are take h1 is this distance, h1 this is the h1 distance, and this is the h2 distance long. So h1 minus h2 is that height you rises. So this is your force. This is the distance you travel to the direction of the force. So yeah, the work done by you is force is mg. The distance you increase is h2 minus h1. That's your s, because the net distance you travel. So they found the net work done is mgh2 minus mgh1. That's your change in potential energy. This is the change in potential energy. Okay. Here, kinetic energy not involved, because we assume that we move the object up. When it comes to the final position, we assume that only potential energy gain, but no change in kinetic energy. That means we're just moving up with a constant velocity. Okay, no change in kinetic energy. So we got mgh2 minus mgh1. So work done is mgh. Okay, if the h1 is 0. If you If you start moving it from the ground, so H1 is 0, so the work done is mgh2. So this is the gain in potential energy. So this is the potential energy formula, mgh. Also derived from what? From work. Yeah, from work, fast time, distance travel. All our energy formula is derived from work originally. Work is the one used to do gain energy. So work done is change in potential energy for this case. The earlier one, kinetic, we proceed the object in flat surface so that EP does not rise. Here we perfectly go up and we move it with a constant velocity so that no gain in EK. Because work done has a tendency to rise the EP and EK. Okay, so here we force the system only rise the EP so that we can find the potential energy formula. Okay. Okay, so again, one easy example. A pump lifts water from a lake large tank 20 meters above the lake. How much work does the pump does pump do as it transfers 5 meter cube of water to the tank? 1 meter cube of water has a mass of 1000 kg. Okay, so there is a lake, so there is a pump rises the water to a tank. Okay, to a tank of a height of how much? To a tank of height of 20 meter. Okay, 20 meter tank. Yes, 20 meter tank. Okay, so the water, 5 meter cube of water, yeah, the pump does as it transfer 5 meter cube. What is the work done when it transfer 5 meter cube of water into this tank? So the work done by the motor, should be equal to what? The work done by the motor, should be equals to the work done gain change to what type of energy towards the end when the water rises up here. It changes to gain in changes in potential energy of the water. Okay, the work done by the pump is actually causes gain in potential energy of the water. So work done by the pump is the change in potential energy of the water. Change in potential energy of water is of course mgh. The initial h is we assume 0 because from the ground. So mgh. So m is up. How much the mass of the water has been raised? 5 meter cube. So it's 5,000. And gravity is 9.81. And the height it rises was 20 meter. Okay, that's this the work done. You should get this energy. Okay, 0.981 joule of megajoule of work has been done by the pump. What is the concept we believe? The work done by the pump equals to the gain in potential energy of the water here. We are assuming the water does not gain kinetic, only gain potential energy. That means just move with a constant speed now. So no gain in kinetic. Okay. So then we conclude this work done by the pump is equals to gain in potential. Then we can find the answer. Okay. Okay, so that is gravitational potential energy formula, mgh. Okay, now we're going to derive elastic potential energy formula. Anyone? What is the elastic potential energy formula you learned last time? Any of you? What is the elastic potential energy of a spring?
Half fx.
Half fx or?
Half kx squared.
Very good. Half kx squared. So now you need to know how you got this formula. So how do you get this formula as the elastic potential energy? So again, we start with work. Suppose an object attached to a spring with a spring K, the spring being pulled by a distance of x. Okay, being by a distance of x. So you pull F, and you extend it for x. So what is the work? Elastic potential energy stored in the spring is the work done by this force. Okay, work done by this force. But spring is different. This force is not constant. This force is changing. For a spring, of course, you know Hooke's law. Spring, if you draw force versus extension for the spring, it's going to be like this. The force applied by here to extend the spring, greater the extension, greater the force need to be applied. So what is work done? the work done by the spring. It will be area under the graph, but now in this case, the area under the graph is of fx. It's of fx. It's not fx. Okay, it's not a constant force. The force is increasing with displacement. So that's why half fx is formula. So the work done by the force is half fx. So work done is the gain in elastic potential energy. So you have to state the first word you have to say is work done, but work done by the spring. Work done by the spring is equals to gain elastic potential energy. Okay, so work done is half fx. F will be kx, so it's going to be half kx squared. Okay, this is the derivation. So you must start deriving. Work done by the spring is the gain in elastic potential energy. Work done is half fx, area under the graph of fx, so half kx squared is formula. So the derivation you have to know. Work done is the gain in elastic potential energy. Work done by the spring is area under the graph of force versus x. This given 1 mark when you give a statement area under the graph f versus x is the work done. Keyword get 1 mark, then half fx. Okay, so the derivations are given importance in A level, which last time you just accept the formula, but you need to know a little deeper how they got the formula. For mgh, half me squared, elastic potential energy. Okay. Okay, so mechanical energy and its conservation. For a mechanical system where total energy consists of kinetic and potential energy, the total energy is Ek plus Ep. Okay, constant. So zero, it changes in Ek. If Ek increased by 5 joule means Ep must decrease by 5 joule. If the system only involving mechanical energy, that means it don't have thrust. You don't have thrust like a car engine. You don't have an engine. It's just like a trolley moving up and down with the act of nature. Then it only works based on mechanical energy. So if it rises a certain height, the trolley, it gains potential 10 joule means it loses kinetic 10 joule with no air resistance involved. No air resistance, the trolley don't have any external force, like don't have engine. Then mechanical energy is conserved. So yeah, if Ek rises, Ep drops with the same amount. Like here, so at A, all in form of potential energy, 10 joule, 0 joule kinetic. Okay, when you come to the bottom, the other way around happens. Kinetic energy becomes 10, potential becomes 0. When you go to the top back, of course, potential gain 10 joule and 0. So mechanical energy is conserved with one assumption: no air resistance, no friction on the track. Then this can be concluded. Okay. So in the D, the D, the potential energy, kinetic energy will be partially 5-5. Okay, it could be partially 5-5. Okay. Okay, sorry. Okay, at E also will be like a mixture. Okay, it'll be a mixture. Okay, so you can see in this diagram that mechanical energy is conserved, and going up, potential energy at the top is the maximum, and go down, kinetic energy become the maximum. You know, this pendulum, the same mechanical energy is conserved if no air resistance. So at the end is the potential energy maximum. When you come to the center, all change to kinetic energy. This, the mgh, is converted to half me squared. The vertical height will have to be used. Same thing. A planet, like let's say a comet, okay, a comet or an asteroid going around the sun, or a planetary system and going around the sun. In reality, the distance the planet makes from the sun is actually not the same. Sometimes, some months it get closer, sometimes it go further. So when the planet get closer to the sun, it gain kinetic, it loses potential. Okay, when it go away, it gain potential and loses kinetic. So the planetary system, when close to sun, it move faster. When go away, it's slower. So mechanical energy is conserved as long as no air resistance. Okay, no friction. Okay. Okay, one question. 2 minutes for you. A 10-gram bullet traveling at 300 meters per second penetrated a block of mass 1 kilogram resting on a frictionless plane. The block with the embedded bullet slides up the inclined plane to stop at point which is at height h above the plane. Calculate the velocity of the combined mass immediately after the impact. Okay, so like the bullet goes up here. So there is a block here. The block is 1 kilogram. It's 1 kilogram. The bullet go and strike the block. The bullet is 10 gram. Okay, the 1 kilogram is in rest. It's in rest. Okay, and the bullet is moving forward with 300 meters per second. Okay, 300 meters per second. Sorry. Okay, so after the bullet collide, what happened? This is the frictionless surface, and this frictionless, no friction, frictionless surface. Okay, no friction. So the block and the bullet rises up this inclined surface at a certain height. The bullet is embedded inside. The bullet is embedded inside. So it rises a certain height of h. Okay, this is the h. Sorry, it's going down. Okay, so this is the question. Now the question: what is the velocity of the combined mass immediately after the impact? After the bullet strikes into the block, what velocity is moved forward? Okay, how do you find this? This is conservation of momentum. You can say it momentum. Okay, you can use the momentum. Then find the height. Conservation of momentum. Yes, A use conservation of momentum. Okay, and this type of question was in the tutorial too. So how do you do? So based on conservation of momentum, then B you use conservation of energy. Okay, give a try. Give me the answer. Anyone? What is the answer for the A? The bullet and the block. After impact, the block and the bullet was moved together with a common velocity v. So how much is the v? The bullet was 300 meters per second, and the block is how much? Is 10 gram. I put in kilogram. Is 0.01 kilogram, and the block is 1 kilogram. Sorry, 1 kilogram. It was in rest. 0 meter per second. So based on conservation of energy is what? The momentum of the bullet 300 times 0.01 plus the momentum of the block, of course, which is 0, is equals to the final momentum. So the both mass together, so it's going to be 1.01 the total mass times the V. Okay, this is your final answer. So V is, yeah, get what? 3 divided by 1.01 is the speed it rises up. Correct? So anyone got the answer? What is the answer you got?
2.97.
2.97. Good. 2.97. 2.97. So when something collide with something and combined velocity, if they ask, the only clue we have is momentum. No choice. Momentum is concept. Okay. Now next comes to this topic. What is the height it rises? So based on conservation of energy, what is that? Changes in EK plus changes in EP must be 0. Must be 0. Changes in EK, changes in EP must be 0. So when it goes up, changes in EK positive or negative? Negative, right? Or you can put like this one. So from this formula, negative changes in EK should be equal to changes in EP. Changes in EP. Negative changes in EK is what? Final EK minus initial EK. Minus initial EK is equals to EP. The final EP lah, MGH EP. Just put MGH. We put it MGH. So we can work out the H now. Okay, but remember here, EK final how much? EK final is how much? EK final is 0. When you climb up to the top, EK final becomes 0. EK initial, we can find out EK initial is half MV squared, but V is how much? 2.97. M is how much? M is the both mass together, 1.01. You get the initial. So you can find the H. Anyone tell me how much the H value you got? How many meter? Calculate for me. 1 minute. Anyone? Yes.
0.45.
0.45. Okay, 0.45 meter. All of you got 0.45 meter. Okay, so this question is conservation of momentum, no choice involved. Conservation of energy is used. Remember, changes in EK plus changes in EP equals 0. Both put one side first. So therefore, negative changes in EK equals to changes in EP. Changes in EK, we always go for final EK minus initial EK. EP also, we go for final EP minus initial EP. Okay, do you have any problem with the sign? Okay, any question from this slide? Oh, no, Okay, so that's about energy and work. Okay, energy and work. Okay, before we go to power, as usual, some questions first. I don't want to go for power yet. Okay, so we go to the questions now. Okay, so you know 2, question 17. What's the answer? What is the work done on this air in one stroke of the pump? Okay, the gas has been compressed. When the gas has been compressed, work has been done. So what is work formula in a compressing gas? P changes in volume. Okay, sorry, P changes in volume. Let me see. Okay, so look at the question. So yeah, so P changes in volume. So what is the answer? Should be C. P V1 minus V2. Okay, V1 minus V2. So from high volume, it dropped to V2. So the area in the graph changes in volume times P is your work done. Okay, so it's supposed to be V2 minus V1, but it's moving from V1 minus V2. Just the magnitude. Okay, V1 minus V2. So C is the best answer. Okay, but the actual answer should be changes in volume is final volume minus initial volume. Final volume is V2, initial volume is V1. So actual answer should be P changes in P in bracket V2 minus V1. That's the actual answer. But in terms of magnitude, which should be the correct answer? C reveal the correct magnitude. P V1 minus V2 or V2 minus V1 give you the same magnitude. So the best answer out of these 4 is C. Okay, so work done. Okay, question 19. Give me the answer. A twig from a tree drops from a 200-meter high cliff onto a beach below. During its fall, 40% of the twig energy is converted into thermal energy. What is the speed with which the twig hits the beach? So what type of energy change to what type of energy? The potential energy is converted to kinetic energy plus thermal energy, right? Okay, so just okay. So what's the answer? So when the twig is on top, it's purely potential. Okay, when it comes to the ground, the potential was converted to what? Converted to EK and also what? Heat. And change to heat. Okay, tell me, if one EP, it's one EP, how many EK become? One EP equals to how many percent tend to become EK? Look at the question. How many percent tend to become EK? 40% is tend to become thermal energy. So 60% is EK. So what number you put here? What number you put here? So the EK is actually how many percent of EP? EK is how many percent of EP? It's only 60%. 60% is 0.6. 0.6. So EK is actually 0.6 of EP was converted. Okay. So this is the point you must realize lah. So EK is 0.6 of the EP. Okay, only 60% of EP is converted to EK, So 0.6 EP lah converted to EK. So now the question asking what is the speed which the twig hit the beach? So EK is half mv squared is equals to 0.6 EP. EP is mgh. So from here you can work out your V. So what's your V? Mass cancels. So your V is what? 1.2 GH square root. 1.2 GH square root. So what's the answer you got? 1.2 times G times H square root. Has anyone got the answer? How many meters per second? What do you get for this? V equals to root of 1.2 times 9.81 times what? Height. Height it was dropped is 200 meter. So this should be your answer. Okay. Does anyone get the answer? How many meter per second? Yeah, class. So 1.2 times 9.81 times 200. Square root. What do you got?
C.
48.5.
48.5. Okay, good. So like around 49 the closest answer. So C should be the answer. Okay. So the keyword here is what? What type of energy change? The potential energy change to kinetic and thermal, but they're asking for the speed. So kinetic energy is how many of potential energy? 0.6 of the potential energy because only 60%. Okay. Okay, good. So this is the today's lesson. So today's lesson, what do you learn? Today's lesson, you learn how kinetic energy is derived, how potential energy is derived, how elastic potential energy derived. You have to know. Okay, how work done by the expanding gas P changes in volume has been derived. That derivation you don't need to know, but you only need to use the work done by the expanding gas is P changes in volume. Okay, so that's what something new you learn lah. How kinetic energy derived, potential and elastic potential energy. Okay, all come from where? Work energy theorem. All the whatever work you've done towards the end is converted to some sort of energy. You need to realize that. You drag a table with a certain force. At the end, the work you've done will convert to some sort of energy. Maybe in form of gain in potential energy if you climb it up, or maybe it gain kinetic energy, or maybe the work you've done used to generate heat. Work done against friction. Yeah. So these are the three sources of energy dissipation. Now, whatever work you've done, it converted to kinetic, potential, or sometimes change to heat. Okay. So these are the three conclusions. Any questions for today's lesson? Okay, class. So we stop here. You can start to do the past years ready partially. Okay, whatever question you manage to give a try. Okay. So the next class we will do the power. Okay, we do the power, and yeah, another two. I think you need 2 hours left to finish this topic.
Sir.
Yeah.
The word file yesterday that you tell us to do the chapter 5.1, I think the mark scheme behind is wrong. Got some problem. The word file.
Oh, which
chapter one? 5. Chapter 5.
The word chapter
file.
5.
The word file, not the past.
Oh, the force, the work.
Yeah.
The work means this topic lah.
I mean last chapter.
Forces.
Yeah.
Forces. Which part you got a problem?
No,
the
word file
the word
that you told us to do. The last part, there are some exercises. The mark scheme, I think there's a problem there.
The mark scheme is not for that questions, right?
Yeah.
Okay. Let me change that lah, because last year also got that problem. Okay. So I try to get done. Okay. Good. Thanks. Okay. So any other questions, guys? Don't have the questions, Okay. So tomorrow we continue with this topic lah. At the background, you try to do more questions. Okay. We stop here. See you then tomorrow.